Dear colleagues, let me introduce our study, Intelligent Information Technology for Business Process Model Quality and Error Volume Assessment. Let's begin with the agenda of this paper. I will present introduction and related work, including state-of-the-art and quality assessment analysis, plus modeling rules, problem statement for this research. Materials and methods include element features, extraction, predicates for modeling rules checking, general approach outline and schema, quality and errability measurement insights, as well as assessment scale. Next, I will present results and discussion, which introduce computational procedure structure, preliminary results, how we weighted BPMN process model elements, quantitative results summary, as well as goods dispatch process example with analysis, measurement, and discussion. And finally, I will present conclusion and future work in this direction. Let's begin with the introduction. As known, a business process is the sequence of structured tasks or activities which are executed in the organizational or information system to achieve specific targets and create a value for the customer. Business processes are visually described using graphical models and diagrams that help all the involved stakeholders to understand, analyze, and improve depicted workflows. Therefore, being the most valuable assets of the business process management methodology, business process models should be of high quality. Only high quality business process models may be useful for the workflow design, analysis, improvement, and activities automation. As part of the related work, we have analyzed the state of the art, and different researchers in this field emphasized visual modeling as central for BPM to depict organizational activities, decisions, and events. They also advocated modeling guidelines to create high quality and understandable process models and formulated general benefits of BPM that include enhanced event monitoring, information control, and efficiency assessment. These all findings resulted into such an insight that business process modeling acts as the communication bridge between technical and business stakeholders, and also visualization of process improves and workflows, improves analysis, capture, and redesign of enterprise activities. Let us consider the rules for consistent business process modeling. They include such statements that start events should have only outgoing flow, intermediate events should have one incoming and one outgoing flow, boundary events should have only one outgoing flow each, and events should have only incoming flows, one for each. Activities that include tasks or sub-process should have one incoming and one outgoing flows each, and gateways should be either splits or joins, which means they should have either one incoming and two outgoing flows for splits or two incoming and one outgoing flows for joins. And based on these findings, we have formulated the problem statement. Let's consider extracted elements from BPMN models as identifiable objects in terms of the intelligence theory. We use the comparator identification method, which is based on predicate logic, and taking any data or signals as input while providing binary values, zeros or ones on output. So the problem includes detection of incorrect elements that violate modeling rules, assessing the impact of different element types on the correctness of BPMN models, measuring the quality and errors volume, and the generation of textual explanations for the detected incorrect BPMN elements. By processing BPMN files of business process models as XML documents, we may obtain structural features or the numbers of incoming and outgoing sequence flows for each business process model elements. Let us consider such process elements in BPMN as OR gateways which demonstrate parallel executions of all actions that met conditions. Sub-process, a complex tasks that can be broken down into smaller parts. Boundary events that may occur during the execution of a specific task. XOR gateways that introduce branching with conditions and only one course of action. Intermediate events, an event that occurs between task executions. Tasks themselves, the units of works that can't be splitted anymore. End events that mark business process completion. Start events that initiate business process execution, and the end or parallel gateways introduce parallel executions of all the actions without preliminary conditions check. So let us consider the predicates for modeling rules checking for all these elements: start events, end events, intermediate events, boundary events, as well as tasks, sub-process, and gateways. And the general approach we introduce includes such steps as business process model elements extraction from XML documents, actually representing BPMN diagrams. Using modeling rules, we then assess business process elements to conformance to these rules and calculate summarized measures as the fault rate. Then using the fault rate, we calculate business process element types weights using Sati's method by completing the judgment matrix and using the well-known pairwise comparison procedure. Then we calculate quality and errors volume measures and define linguistic quality and errability values and transform them as textual explanations on the quality and errability of business process models under analysis. Let us define the business process model quality as the degree to which business process elements of different types fulfill the modeling rules in accordance with the ISO 9001 definition. So here it becomes possible not only to measure quality, but also to assess the volume of business process modeling errors, or in other words, as we propose, the errability of a BPMN model. Here we operate with the subsets of business process elements of different types extracted from the BPMN model under analysis and consider them to calculate both Q measure for the quality and V measure for the volume of errors or the errability. And let us apply the Harrington scale and desirability function to introduce business process models quality and errability levels. There are 5 levels as very bad, bad, satisfactory, good, and very good levels for process modeling rules fulfillment or the quality, and very low, low, moderate, high, and very high levels of business process modeling errability. And these linguistic variables are also used to build textual explanations on the current state of each analyzed BPMN model. So let's consider the computational procedure. It includes such step as extraction of process elements and their properties or features from BPMN files by processing them as XML documents, assessment of each extracted process element in terms of its correspondence to modeling rules, calculation of summarized measures by each type, the number of faulty process elements, and the fault rate of business process elements in general. and then calculation of weights for each of business process element types using the SATIS pairwise comparison method, and filling the judgment matrix using the fault rates. Finally, then we do assessment of business process models quality and errors volume using the introduced measures, and obtaining the linguistic variables for business process models quality and errors volume to explain the obtained results and analyze them. The experiments were performed using the Camundus company open GitHub repository of 3,729 BPMN files, out of which 3,722 were successfully processed, but 7 remained with some processing errors, meaning the files were broken. So we introduce here and calculation for the distribution of business process element types, showing that tasks demonstrate the most common elements in BPMN models. The error frequency of business process element types show that XOR gateways and tasks are the most error-prone BPMN elements. And the fault rate by business process element types show that there are sub-process and boundary events demonstrating the highest fault rate, then AND gateways, OR gateways, and XOR gateways demonstrate also close fault rates, but the remaining types of BPMN elements, such as intermediate events, tasks, end events, and start events, show relatively lower fault rate measures. Using the fault rate measures, we have built the judgment matrix and applied SATIS pairwise comparison method to obtain the weights of BPMN element types calculated using the well-known SATIS computational procedure. And then, as we can see, we summarized the obtained results of BPMN models processing and analysis, introducing the distribution of business process models by quality value ranges, which shows that 265 models are lying between 0.95 and 1 for the quality scale, and 1,044 models lying in the range of from 0.9 to 0.95 in terms of quality measure, and the remaining models are distributed by other intervals. And also we calculated the distribution of business process models by errorability, showing the exactly opposite distribution. We have also complete the exploratory analysis results for quality and errorability measures and find out that the minimum quality measure for analyzed BPMN models is 0.49, and the 25% of models are above the 0.94 measure rate. For the quality, median value is 0.96, and other 25% upper the Q3 75 percentile is equal or greater than 0.99. And errorability shows that maximum errorability rate is 0.50, with 25% of models above 75 percentile having the errorability greater than 0.06, with a median of 0.04 and the 25 percentile of 0.01. And the more understandable distributions of business process models by quality and errorability levels shows, according to the Harrington scale, that we have 3,613 models of very good quality between 0.8 and 1. Only 106 models belong to the good ones in the range for the quality between 0.63 and 0.8. And only 3 BPMN models are estimated as satisfactory quality, lying in the range between 0.37 and 0.63. However, the errorability levels demonstrate the opposite results. We have 3 models of moderate errorability, 106 models of low errorability, and 3,613 models of very low errorability. And finally, let's consider the goods dispatch process example. We have calculated quality measures of this sample business process model demonstrated on the slide, and with the detected errors showing that, for example, here start event has 2 outgoing flows. We have activity named collect parcel insurance without any incoming or outgoing flows. Pick the goods task also doesn't have any incoming flows breaking the workflow. The end event has 2 incoming flows, making the unclear and inconsistent the branching inside the process scenarios. And also we have the end gateway demonstrated as error number 3, which has only one input, but it either no split or join. It doesn't have any outgoing flows. So we have analyzed this model using the proposed approach and developed software in Python. And we can conclude that the sample model's quality and errorability measures are estimated at 0.77 for quality and 0.23 for errorability, respectively, while in compared to the more straightforward measures like number of error elements and number of correct elements and incorrect elements, as we denoted here as CER and IER, they demonstrate values of 0.64 and 0.36 being more rough and doesn't take into account any weights of different BPMN models, as we have previously calculated using the SATIS pairwise comparison procedure. So the proposed approach and intelligent software we implemented in Python allowed us to extract BPMN elements and detect incorrect ones that broke modeling rules, assess impact of different BPMN element types on business process model correctness, assess business process models quality and errorability levels as numerical measures, as well as linguistic variables that correspond to different levels, and provide textual explanations for the detected incorrect BPMN elements to assist the users who are in response for building that models. The results of computational experiments with almost 3,800 Camundus BPMN models were analyzed and discussed, and it's possible for us to assume the ability of considered intelligent technology to efficiently handle large enterprise business process models repositories and further apply them to the analysis of real-world BPMN models. In the future work, we plan to use advanced intelligent techniques like fuzzy logic and comparator networks to improve the thinking capabilities of the proposed intelligent technology. We also assume the deeper analysis of BPMN elements like various events behavior, data stores, poles and lanes, as well as message flows to consider collaborative models. And we also will consider business process semantics, which is also in plans for the future work. Thank you very much for your attention, and I'll be glad to answer all your questions.